3.3 Stretching and compressing graphs of functions. Okay, so we have this value a, and it's going to be in front of our x squared. So what we're going to do is we're going to just do a bunch of different stretches and compressions and see what happens with the shapes. Okay, so if I was to do a normal x squared function, we would go one space over, this isn't what I wanted, this is just x. Okay, let's do y equals x squared. So if I went 1 over, I would go up 1. So 1 squared is 1. 2 squared is 4. 3 squared is 9. So we should all be pretty confident graphing a normal parabola that has not been transformed in any way. It's like a basic parabola. There it is. Okay, that's if a is 1. If I plug in a to be 2, what that does is it doubles any of these values. So instead of it being 1, it's going to be 2, 4 turns into 8, 9 turns into 18. So if I go one space away from my vertex, I'm going to go up 2. 1 second. Okay, I just graphed that in there a little bit tighter. Okay, so it should look like this. And what happens to it is it becomes more skinny. It stretches and becomes thinner. So anytime you have an a value that is bigger than 1, then it becomes a stretch. So this has a vertical stretch. Okay, let's go with 0.5. So we're going to manipulate these original ones by timesing them by a half. So it'll be 0.5 to 4.5. So I'm going to go over 1, up a half, over 2, up 2, over 3, up 4.5. So what you should notice about this is it has become wider. So we call that a vertical compression. And it's by a factor of a half, and we can tell that it's going to be a compression because it's between 0 and 1. Okay, now let's do -2. So from last lesson, you should know that it's going to have a reflection. So what it is it's going to look exactly like this graph, but it's going to be reflecting downwards. So instead of going over 1 up 2, we're going over 1 down 2. And then over 2 down 8. So this graph, oops, I don't know how I got that blue line there. There we go. This graph will look like this. So it's the mirror image of that 2x squared. And same with the -0.5 x squared. It's going to look exactly like our red graph, except it's going to be opening downwards. So your a value determines what direction the parabola opens, and it determines the stretch or compression. And again, a stretch is when your a value is bigger than 1 or less than -1, and it is a compression if it's between 0 and 1 or 0 and -1. We can apply this knowledge to any type of function. So let's look at this graph. We have f of x, and we have some points x and y, and then we have -1/4 f of x. So my a value is -1/4, which means that I have a vertical compression, because it's between 0 and 1. And we also have a reflection. And because it affects our y values, it's on the x-axis. So looking at our points, the a value is always going to affect our y value. So x is not changing, but our y value is going to be multiplied by -1/4. Okay, so we got some points here. We have 1 and 1. We have 2 and 2. We have -1, -1, and +1, I mean. -2, +2. And if you're unsure of what type of graph this is an absolute value graph. Okay, so our new points will be at 1 and -1/4. They'll be at 2 and 2 times a quarter, -1/4, which is -1/2. And we'll also have 1 at 1 and -1 and -1/4, and -2 and -1/2. So looking at this graph, we have a point at 1 and -1/4, which would be down here. We have a point at 2 and -1/2, which would be right here. And then we have it on the other side as well. So our graph, we could probably throw a 3 in here so we can see it. So we have a graph at 3 and 3. So we'll have a graph at 3 and -3/4. So it is going down. And I put this one in the wrong spot. And this one. So it looks like this. So you should notice that it is skinnier and, or not skinnier, it's wider, the opposite of skinnier. Skinnier is for a stretch, wider is for a compression. Looking at our domain and range for our original function, my domain would be x is an element of the real numbers, and my range would be y is greater than or equal to 0. For my green function, the changed function, my domain would be the same, it doesn't change. And our range would be now less than 0. Alright. Okay, let's do some horizontal stretch and compressions now too. Okay, we're going to do a radical function, and we're going to do the square root of x. So let's start with just that. F of x is the square root of x. So x, y, actually I should be doing this, that's fine. Okay, so if I plug a 1 in, I have the square root of 1, which is 1. If I plug a 2 in, I have the square root of 2, which is like 1.4. If I plug in, let's go with 4, because I know I can take the square root of 4, I get 2. So our points would look here at 0, 1 and 1, and 4 and 2. So my original square root of x function looks like this. So let's see what we can do when we add some variables in for b. So let's do the square root of 2x. So if I plug a y in here, or x to be 1 here, I would have square root of 2 times 1, which is the square root of 2. If I plug in a 2, I get the square root of 2 times 2, which is 4. So if you notice, this point is right there. That's kind of handy. And let's see if we can make this point up here. If I plug a 0.5 in, the square root of 2 times 0.5 is 1, which would get us that square root of 1. So that's how I could kind of make those related points. So what that means is that at 0.5, it's going to hit 1. So it's closer to the line. There we go. And at 2, this is supposed to say 2. The square root of 2 times 2 is 4. The square root of that is 2. 2 and 2, we have a point. So what you should see is that this graph is shorter. So it's actually a horizontal compression. And it's half the size. So this one went from 4 and then it went to 2. This one went from 1 and it went to a half. It looks like it's half the size. So knowing that this is 2 helps us with that. So let's do another one. Let's do 0.5. So if I plug a 1 in, I would get the square root of 0.5 times 1, so the square root of 0.5. Not so useful. Let's plug a 2 in. If I do the square root of 2 times 0.5, I get 1. The square root of 1, which is 1. So if you're noticing, to get this 1, I have to take this number and double it. So if I wanted to figure out what this number was, I would double it. So let's go 8. So I would go 2 times 4, 8 is 16, which is 4. And I meant to do a half. I'm still thinking of the last question. I'm sorry. 0.5 times 8 is 4, and the square root of 4 is 2. So this one would look, at 2 we hit 1, and at 8 we hit 2. So it actually makes it wider. So this is actually a horizontal stretch. And if you noticed, this one is a horizontal compression by a factor of a half. Everything was 1 over 2. This one is a horizontal stretch by a factor of 2. Okay, and if I wanted to do this negative 0.5 half, or negative 0.5x, it's going to be the same as this graph, but reflected on the y-axis. So it would go over 1, and it would go over negative square root of 0.5. It would go over 2 and down 1. Just kidding, I have that backwards. It affects your x values. What am I talking about? Because the negative sign is on the inside, these ones would become negative. So negative 2 would become 1, negative 8 would become 2. So this one would look like this. So anytime that that negative is on the inside, remember that is a reflection on the y-axis, which means our x values would turn into be negative. Okay, so what you should be noticing, just 1 second, I'm going to pause this. In our original equation, it was x and y. When it became 2x, let's go 1 and 1. So our original point was 1 and 1. When we plugged it into the equation for root 2 of x, it became 0.5 and 1. That's how we still got that 1 value. When we plugged it into the square root of x, to get 1, it needed to be 2 times 1. When we plugged it into negative 0.5x, in order for it to be at 1, it would be at negative 2 and 1. So those are all kind of common because they all have that 1 value as our y value. if I was to plug it into the square root of b times x, our y value doesn't change, and our x value changes by a factor of 1 over b. So not by 2, but by 1 over 2. Not by 1 over 2, but 2 over 1. So you do the reciprocal to figure out what that stretch or compression is going to be. So let's do a practice question. We're going to do g of x is 0.5 of x. So our b value is 1 over 2, which is 0.5. So we are going to have a horizontal stretch. And I know it's a stretch because for horizontals, between 0 and 1, it's a stretch, and outside of 1, it is a compression. And it's going to be by a factor of 2. So the reciprocal of this. Okay, so we'll do g of x, which is just a normal x and y point, and then we'll do g of 0.5x. And the way that this is affected is our x value is doubled. So by that factor of 2, we're going to double our x values. So in our graph, we have points at -3 and 2, -1 and 5. I should look at the screen as I'm writing. 3 and 3, and 4 and -2. Quickly, before I move on, let's do the domain and range of this function. It looks like the farthest to the left it can go is -3. So -3 is less than or equal to x, which is less than or equal to 4, which is over here. For real numbers. Our range, our lowest y value is -2, and our highest y value is 5. Okay, back to this. We have our points. We're going to change it by doubling our x values. So this will become -6 and 2, -2 and 5, 6 and 3, and 8 and -2. And now we just go and we plot them. So we have -6 and 2, -2 and 5, 6 and 3, 8 and -2, and then we can connect. So it is wider. My domain now has been stretched for our x values. It goes from -6 to 8, so we double each of these. And our range has not changed. It stays the same. Okay, this one has 2 types of compressions. So we're going to start by finding the domain and range of this function, because I always forget to do that first. So domain is x needs to be greater than or equal to -2. And our range is that it has to be greater than or equal to 0. Now let's make our table of values. So that our normal points are x and y, that is for f of x. And for 4f and -0.5x, let's decide what types of transformations we have. So we know that this is going to make it have a vertical stretch by a factor of 4. We know that this is going to make it have a horizontal stretch by a factor of 2, the reciprocal. And because the inside is negative, we're going to have a reflection. And because our x values are the ones that are going to be changed, it'll be a reflection in the y-axis. So there's all of our transformations. So our new point for 4f of -0.5x is going to be at -2x and +4y. That is our new point. So we have a point at -2 and 0, and it also looks like we got a point at, let's go with this one, 2 and 2. So we're going to just manipulate using the formula we just had. So we have -2 times -2 becomes +4. 4 times 0 is 0. And 2 times -2 is -4. And 2 times 4 is 8. So our new point will be at 4 and 0, and -4 and +8. And here is our graph. So our new domain, we want x to be less than or equal to 4. What am I doing? X is an element of the real numbers. And our range, we just want it to be greater than 0 for all the real numbers. Alright, that's how you do multiple transformations. If you do this and you manipulate the points every time, it's going to be really easy. Okay, last one, determining an equation after a transformation. So this is for a transformation that has only had compressions or stretches. So let's start by figuring out points that are the same on both graphs. We'll call it g of x. And the point that we look for g of x is x over b and a times y. Okay, so we have 0 and 0. That doesn't change on either of them. So that is not useful. We do have intercepts here. So we have an intercept at -2 and 0. And now we have an intercept over here at -1 and 0. We have an intercept at, it looks like 1 and 0. And then it looks like it's at 2 and 0 over here. So really what you want to just have is you want to have 2 points, or 1 point that'll show you how it gets manipulated from one thing to the next. And if we, oh, I see what the problem is here. This function right here is my f of x. And this function right here is g of x, in case you were wondering about that. I didn't realize that the x-axis was going up by something other than 1. So this point here at 1 and 0 is actually the same as 0.5 and 0. There we go, that makes more sense. Okay, so right now we could probably figure out what our x stretch is, because we could go from what's this to this and what's this to this. It's pretty basic. But we can't actually figure out our y values because all of them are zeros. So we need to pick a point that is not 0. So I'm going to go to this little bottom part right here. So this bottom point looks like it's at -1.5, and it's almost -3. Like, let's go -2.75. Maybe 2.8. It doesn't matter. It's close enough. The next point that the other point where it hits that is going to be at -0.75, it looks like. So half of that. And that also looks like about 0.75. Okay, so now we should be able to figure out our compressions and stretches. So I know that x over b is equal to x prime. So what that means is if I take my original x and I divide it by b, it gives us the new x in the new function. So let's look at an x value. It can be any of these. So if I go from -2 and divide it by b, it becomes -1. And then I can switch the places with this. and we'd have negative 2 over negative 1 equals b, so 2 is my b value. We can't use this any of the other points except for this one for y, but same concept here. A times y, if I take y, my original y, and times it by my a value, it becomes a new y. So if I take negative 2.75 and times it by a, it becomes negative 0.75. And then I'm going to divide both sides by this. And really, it's going to give you a decimal. You can just leave it as 0.75 over 2.75. You can get rid of the negatives because it's positive. So my image graph, we can plug it into the formula of g of x is equal to a f of b times x. There we go. So my equation would be I don't know where to write this. I'm going to do this. I'll write it up here. G of x is equal to a 0.75 over 2.75 f of b, which is 2, so 2x. So there's my equation. Now this is you can only do it this way because it's only been stretched and compressed. It hasn't been translated in any ways. So yeah, there you go. Stretches and compressions. That was a hefty lesson. Alright, on to the next one. Bye.